So let's look a little more closely at this notation. Because just like when we learn derivatives, we're not going to use, the Riemann sum eventually. For chapter 5, yeah, we will. But eventually we're going to use this notation strictly because this is the streamlined version or the more accurate version. So we need to now pay more attention to what this all means. So again, this right here is meaning a sum, an infinite sum of infinitely many rectangles between A and B. This right here is referring to the function, which is the height of each rectangle. This right here is our calculus difference in x, which is the base of each rectangle. The word used for the function is called the integrand. So you might hear that. And again, that's the height. This right here, the dx, is the change in x. It's also called the variable of integration. So it's the integral of f of x with respect to x. Similar to how we used to do dy dx was the derivative of y with respect to x. This is the integral of f with respect to x. So it's also telling us the variable of integration. And if you were to read this out loud, it would be read as the integral of f with respect to x from A to B. And we call this a definite integral because it's an actual area. So this is actually equal to a number. You would get a number answer, and it's the area between f of x and the x-axis. Okay? Well, that was something separate. So this means, so your answer for this is equal to a number. And that number is the area between this curve and the x-axis. So you would get a numerical value. And maybe I'll write that here. There would be no more x's or anything in your answer. It would be a numerical value. Okay, one other thing to sort of tell you is that when you have found the value of this integral, when you have found the value of the integral, then you have quote unquote evaluated the integral. So that's what it means to evaluate an integral, is to find the numerical value that this is equal to. And then I just wanted to point out, this here is called a dummy variable because you could call it anything. I could say, okay, the integral from a to b of f of x dx. That is no different than if I said, okay, the integral from a to b of f of t dt. Doesn't matter what I call that thing. Or I could call it the integral from a to b of f of s ds. Or the integral from a to b of f of u du. Okay, you get the idea. But I just wanted to point out, we call this a dummy variable not because it's a dummy, but because it doesn't have any significance. You can call it whatever you want. It still will be the area between f and the x-axis. Okay, so yeah, so one last time I wanted to summarize this integral from a to b of f of x dx is equal to the area between f of x and the x-axis. I know I've said it like a million times because that's so important. And you'll see now as we basically start heading into the examples, so for today's lesson, we're going to find integrals by using area formulas. It's not until 5.3 that we're going to find areas using integrals. Okay, so if you're asked to evaluate an integral, you are always welcome to use area formulas. And you'll see what I mean as we get on to like 2 and 3 and so on. But let's look really quick at number 1. I have seen this kind of question on an AP test before because they want to see if you remember the original meaning of an integral. So this is one of those things where you've got to study the definitions of things, kind of like how we used to use formal definition of a derivative. And then we started using, formulas and rules for derivatives and kind of forgot the formal definition. Well, you've seen the kind of questions that put it back into the formal definition form. They do the same thing with integrals. So we have to remember that this right here means sum. This right here is the number of rectangles. That right there is the largest, I guess I'll just call it the largest rectangle. Really, it's the largest change in x, but that produces the largest rectangle. The largest rectangle is approaching 0. That means so are all the other ones, like the largest base. The largest base of a rectangle is approaching 0. That forces the other bases to approach 0. That means we have infinitely many rectangles. That means an integral. The ck is an x value. The delta x is the same as dx. So I can see that this right here, this f of ck is ck squared minus 3ck. So if I want to translate that into f of x, then I would have x squared minus 3x. So that f of ck now becomes f of x. This delta x is going to become dx when I put it into the integral form. And that's all that this means. This means it's no longer a finite sum, it's now an infinite sum. So this allows us to use the integral sign. And then that -7 would be my a, and the 5 would be my b. So the final answer, I'm going to use the integral sign since I have a limit as the largest rectangle approaches 0, meaning I have infinitely many rectangles. So it's an infinite sum between -7 and 5 of f of x, which we determined was x squared minus 3x dx. And so there's our answer. So this sum is equivalent to that integral. That is not an easy idea to master, so I have a feeling some of you are probably like, what the heck is she talking about? Study that. Go back to the definition on page 1 and compare the two to each other. It's very important that you never forget what this means. It comes from a sum. Okay, so that was example 1. Example 2, notice the wording. It says use the graph of the integrand, which is the function inside, and areas to evaluate this integral. So remember, this means the area between f of x and the x-axis. Okay, so I need to first sketch the graph. This is where all that pre-calc comes in handy. So if you still have it, you should bust out your function books or your cosmic catalogs from last year, because you got to know how to graph that. Of course, this one's nice. It's just a straight line. So we'll go ahead and sketch a graph, and it's between 1/2 and 3/2. So it has a y-intercept of 4 and a slope of -2. So I'm going to go down 2 and over 1, down 2 and over 1, and that's probably enough since my interval is only between 1/2 and 3/2. So here's 1/2 and here's 3/2. And so I'm going to draw the lines. And so basically what I'm trying to do is find this area. Okay, so again, in 5-3, we're going to learn another trick. But for right now, we're just going to simply use area. So that I will finish this problem in the next video.